All right, so we're going to get restarted, and I'm sure people will trickle in as we proceed. So in the morning we came up with those Hamiltonian definitions for mass, linear momentum, and angular momentum, and the ones that I'll keep here are just mass and angular momentum. So the idea here was to recognize that the Hamiltonian, when you evaluate it for a solution to the field equations, is something that's given entirely in terms of a boundary term. And in that boundary term, you have the freedom of setting the lapse and the shift to whatever values you want. And if you pick those values, well, you pick a flow, and that flow could represent an asymptotic time translation. It could represent an asymptotic translation, spatial translation. It could represent an asymptotic rotation. And depending on what you choose, well, you get those Hamiltonian quantities that have the interpretation of, energy in the case of time translations, linear momentum in the case of spatial translations, and angular momentum in the case of asymptotic rotations. And we end up with formulas like these, which says that, a candidate formal definition for the total mass energy in a spacetime would be obtained by integrating this thing over here, the trace of the extrinsic curvature on the two surface as embedded in that three surface, minus the same thing but embedded in flat space-time. You take that, you integrate over the boundary, you push the boundary all the way to infinity, and that is what the Hamiltonian would suggest is a sensible definition for the total mass energy of the space-time. And then for rotations, what you would have is you would select an axis of rotation, you would construct a vector that describes a flow, a rotational flow around that axis. That's this vector over here. And what you would do is to take the extrinsic curvature of the three surface minus this term. You would dot that with the angular, the generator of the rotation. You would multiply that by the normal to the ST surface. And again, you would push the boundary to infinity, do the integral, and that, again, the claim is that this is a Hamiltonian. This is what the Hamiltonian would suggest is a sensible definition for total angular momentum. So I want to discuss this, and I want to, I'll make a few comments about this, but most of all, I want to check that those are really sensible definitions, that, if we had other notions of what a mass is and what an angular momentum is, more operational definitions, things that really represent, our physical understanding of what mass does and what angular momentum does, that this, in fact, does reproduce those notions so that there's no discrepancy between these formal definitions and what we might have on the operational side of this. One remark that I'll make first before I go into that, so before I do the calculation, one remark that I'll make here, and I think it's probably the most important of all, is the fact that these quantities are defined in terms of surface integrals. And as such, they're very robust, and they care very little about what's happening in the depth of the bulk in the spacetime. Really, what matters here is the asymptotic aspect of the spacetime. We are looking at this surface as we push it to infinity. So this will carry an imprint of what's happening in the bulk, but it will be a very robust, very coarse-grained imprint of what's going on in the bulk, because only the asymptotic details of the spacetime matter in these constructions. And I find that very compelling because that tells us that essentially mass and angular momentum and also linear momentum are really properties of the asymptotic portion, the asymptotic structure of spacetime, much more than anything that has to do with what's going on deep in the depth of the spacetime. Of course, there's a relationship. You don't have mass if you don't have something in the bulk of the spacetime, so you need to have something in there. But the point is that, well, what that something is can be very different from spacetime to spacetime, but all those spacetimes might have exactly the same mass and the same angular momentum. So basically, the nature of the mass, the way it's constituted, is something that has no bearing on what the value of the mass is, and the value of the mass is something that's really encoded only in the asymptotic structure of your metric, the asymptotic structure of the spacetime. So what I'm trying to say here is that, it doesn't matter what makes up the mass. It doesn't matter that the mass comes mostly from, baryonic mass in the case of a neutron star, or gravitational binding energy, or kinetic energy in the case of an imploding star. All of those forms of energy will contribute to the total mass. The total mass will incorporate all of this, and it will tell you what the full package is. It will never tell you what the mass is made out of. It will never tell you that it's broken down into kinetic energy, binding energy, nuclear energy, thermal energy, and all of those possible types of energy that you might have, in the bulk of the space-time. This is not completely, new, because we've seen situations like that before. And in fact, when we think even of, electromagnetism, it's not unusual to construct, to calculate the total charge associated with the charge distribution by, constructing a surface as far away from the charge distribution as we want, and calculate the charge by constructing the Gaussian integral on that surface. So even for E&M, you can have a distribution of charge over here. It can be as complicated as you want it to be. But to calculate the total charge, all you have to do is to calculate the electric field on the boundary. And all you have to do to calculate the electric charge is to construct the surface integral of the electric field around that surface. And then you can imagine taking that surface to go all the way to infinity, in which case you would have the total charge in the space-time, and none of this depends on the shape of the surface. And if the surface is extended all the way to infinity, you will capture all the charge that lives in your space-time, all the charge that lives inside that boundary surface. So the idea of using a surface integral to define things like mass angular momentum is something that, well, in fact, comes straight out of E&M. So there's something, there's nothing radically new about this. We're just importing those ideas. So this is something that would have a direct analog in Newtonian gravity, and now we see that it also has a direct analog in GR. So bottom line is that quantities like this that really refer to conserved, global quantities of your space-time are fundamentally defined in terms of surface integrals. That's really the starting point. In E&M, we know that we can also, calculate the total charge by integrating the charge density over, over the three-dimensional volume occupied by that charge density. So certainly there is a relationship between the surface integral definition of charge and the volume integral definition of charge. Maxwell's equations guarantee that those definitions are the same. In GR, as we talked about briefly this morning, we're going to have to look into whether we can relate this surface integral to volume integral type definitions. And the bottom line answer is that you can do it in specific cases. You can do it under some conditions, but you cannot do it generally speaking. So in the general case, this is sufficient, this is all you need, and this is all you've got. So, so in the general case, really, it's the surface integral that wins. You may not be able to relate this to any well-defined volume integral. Even in E&M, there would be a difficulty in trying to extend the volume definition of charge too far. What if that distribution of charge were inside a black hole? If you were inside a black hole, if the charge density were inside a black hole, at least partially, well, you would have trouble going inside a black hole, calculate the density of charge there, and constructing the volume integral of that charge density from the inside of the black hole to the outside to all the way to infinity. So when you're dealing with situations like this, when you're dealing with singular distributions of charge, for example, if the charge is a delta function, well, then defining the density might be something a little bit tricky. The surface definition will always take care of these things. The surface definition doesn't care whether this is inside a black hole or not. The surface definition will always, incorporate all the charge that you have. So even in the E&M case, of course, here I'm applying E&M to a curved space-time situation with an event horizon. what you will find in E&M is that the surface definition is always much more robust. The surface definition doesn't care about the details of the interior. The volume, the volume integral over a charge density definition cares about all those details, and sometimes those details are inaccessible because you would have to go inside the event horizon to find what they are. So bottom line, I think there's something very, superior about, surface integral type definitions for these global quantities. Those really don't care all that much about the inside, and you don't need to provide all of that information to calculate these things. So this is much better than any definition involving involving a volume integral. Nevertheless, I'll come back to that question, and we'll look into the relationship and what the conditions are required for a relationship to exist between a surface definition like this versus, a possible volume definition. All right, so now let's confront this to other notions we might have for what a mass is and what an angular momentum is. And while we have some, pretty specific ideas of what these things do, and in GR we know, for example, that a mass is something that's going to have an attractive power. I can identify the mass of a space-time by looking at how particles orbit around that mass, and I can read off the mass from, say, the orbital period of my orbiting body if I know what, at what distance the orbit is. So if I set up a nice, careful circular orbit at, a safe distance from my body, I know the distance, I know the period, I can read off the mass from this. That would be an operational definition for mass. And it's better be, it better be the case that this operational definition for mass would agree with this formal definition. The claim is that it does, so my claim is that yes, they do agree, and I'll show you how to prove that in this discussion. For angular momentum, well, we also have some pretty specific ideas of what angular momentum does, at least in a GR context. So in any context, well, we know if we have angular momentum if we see things rotating in the space-time. And in GR, we know how to measure angular momentum because what angular momentum does in a space-time is to produce a dragging of inertial frames. So if you fall radially toward a rotating black hole or any other rotating object in GR, you will find that you will be dragged along with the rotation of the body. And you can basically measure angular momentum by measuring this rotational motion that you acquire just by virtue of falling in toward an object that has angular momentum. So for a Kerr black hole, that's a well-known effect, but it's an effect that that is associated with any body that has angular momentum. So how do we express all of this? Well, the idea is that all of those operational definitions for mass and angular momentum, again, they will care, they can be inferred, they can be dealt with by looking at what happens far away from a body that has both mass and angular momentum. So what you can do is to set up a metric that will describe a body like this. And if you're far enough from the body, all you have to do is to solve the Einstein field equations in vacuum. But you can also do it approximately because you're far enough from the body so that, its gravity is pretty weak. So in fact, it's good enough for this purpose to set up a metric that is a solution to the linearized Einstein field equations. And the idea here is that while you're far enough from the body, gravity is weak. You imagine that the body is, settled down so that there's no time dependence going on, at least, asymptotically far away from the body. So all you have to do now is to look for a stationary solution to the linearized Einstein field equations far enough from the body. And that's something that ends up being a very useful exercise. So, and I can just write down the solution. So, so a solution to the linearized Einstein field equations in vacuum far away from a stationary body. So I'll specialize myself to bodies that don't have a lot of time dependence in them. Well, can be written in the following form. So that's a simple exercise of solving the linearized field equation. So you set up the usual type of gauge conditions to simplify the form of the equation, and you end up, with a whole bunch of Laplacian equations. And the solution you get is something that will look like this. So there's going to be a GTT term that will depend on a mass parameter. I'm calling it little m to distinguish it in principle from that big M. And then there would be higher order terms here that we ignore in the linearized theory. Then there would be a spatial part to the metric. So they're still going on with that pie eating contest. There would be a spatial component to the metric that also involves the same mass parameter, m over r, plus higher order corrections. And then there would also be off-diagonal terms that would come from angular momentum. So here I'll just write them as 4j sine squared theta divided by r, and then there would be higher order terms here. And that's the off-diagonal term that corresponds to the angular momentum term, and that's the term that would be responsible in the metric for describing the dragging of inertial frames. And here you attach a parameter to it that would be recognized as the angular momentum parameter for that spacetime as operationally defined in terms of this dragging of inertial frames. So at this point, the statement is that, well, this is a valid solution to the field equations in a vacuum region far away from your body. The body has both a mass and an angular momentum. It rotates and it gravitates. And the statement on top of this is to say that, well, there exists a coordinate system where the metric of such a body can be put in this form. So if you're going to come up with an operational definition for mass and angular momentum, what you could do is to say, okay, I'm going to get started with that metric. I have two parameters in that metric, and I'm going to try to assign a physical meaning to those parameters by looking at effects going on in that space-time that would reveal what those parameters are. And that's how, for example, we recognize that this is really a good notion of a mass parameter for the space-time, because if you look at the geodesic equations for particles moving in that space-time, you look at orbits, you find that orbits will satisfy, at least asymptotically, the equations of Keplerian motion. To leading order, you'll get the Newtonian equations out. You'll get corrections to this, but asymptotically they become very small. And by for example, looking at Kepler's law and identifying the relationship between the orbital radius and its period, you would be able to read off the mass. And that assignment would basically be saying that, well, the mass parameter that occurs here is the same mass parameter that occurs in Kepler's law in Newtonian physics. And in this limit where we look at what's going on far away where gravity is weak, well, there's no better definition for what mass is than this operational definition in terms of Kepler's law. So that's how you would do it for M. So I'll skip the details because I think it's very straightforward. And you would come up with a different protocol here to look at dragging of inertial frames type effects. You would look at those rotational effects in that space-time, and you would basically associate that with angular momentum. And again, there would be no better operational definition for what angular momentum is in terms of physical effects that you would identify coming from this metric, coming from especially the off-diagonal terms. So M and J defined in terms of that metric give operational definitions for mass and angular momentum in terms of precise physical processes. So that way of doing things is pretty good on a physical basis, and it's pretty compelling on a physical basis. And that's a procedure that can be repeated basically no matter what the metric is. So basically, in some other application, you might end up with a metric that doesn't take this form because it's been presented in a different coordinate system. But through, again, looking at the physical processes, going on in that space-time, you would be able to recognize that some parameter in the metric really corresponds to this mass. Some other parameter in the metric does correspond to that J. And by, again, implicating the metric in those, physical processes, by looking at what the physical processes look like as described in terms of, whatever coordinate system you work with, in whatever metric you work with, you would be able to read off from your space-time, from your metric, what is the combination of parameters that gives rise to mass, and what combination of parameters would give rise to angular momentum. So the only drawback in doing it is this. I mean, this is very compelling, again, on physical grounds, and it's always very good to have operational definitions for things. The only drawback is that while it may require quite a bit of work to go through all of this. So for example, if you're presented with a metric in the asymptotic region that looks nothing like this because you've used a very strange coordinate system, or it's just the way that it is, it might be difficult to, to construct a coordinate transformation that takes you back to this form, for example, or it might be difficult to actually, do the description of orbital motion or do the description of, rotational effects. It might require a lot of work every time to boil it down to something that can be recognized in terms of physically relevant parameters. So sometimes, metrics have a way of disguising themselves in funny ways, and parameters that occur in the metric may not be what they seem to be. Sometimes you have to be a little bit cautious. An M may not be a mass, a J may not be an angular momentum. You really have to be careful and make sure that the physical interpretation has been done properly. The beauty of those definitions is that, first of all, they don't care about coordinate systems. They're completely invariant on the coordinate transformations. They involve a bunch of scalar quantities or a bunch of tensorial quantities, but basically those are prescriptions you can use regardless of the coordinate system. So if we happen to find agreement between this and little m and big J and little j, then the point is that knowing how to do the work once and for all in this coordinate system, we validate those as equivalent to the operational definitions, and we don't have to do it ever again. And now when you come with your own metric and you're presented with a metric that looks strange in a strange coordinate system with funny parameters in them, well, you don't have to do all of this work of looking at physical processes and interpreting the metric. You can just plug the metric into this calculation, and it will return the actual mass and the actual angular momentum. So basically, this correspondence between the operational quantities and the formal quantities is something you can do once and for all using this expression for the metric asymptotic, for the asymptotic metric. And once you've done the work once and for all, the point is that you now understand that those are not just formal definitions. Those actually have operational meaning because you understand how to connect them to the operational definitions. So in the book, I go through the calculation. I think I'll skip that here. I think we've done enough long calculations for the time being. But in the book, it's just a very simple exercise of taking this metric, looking at a surface of constant t, looking at a surface, a two-surface of constant r, evaluating all of those things, doing the embedding, calculating the extrinsic curvature, and doing all the steps in that calculation. So it's very straightforward. And as a result of that calculation, you find that sure enough, m turns out to be identical to m, j turns out to be identical to j. And that is the validation stage where we claim now that once and for all, we have established the connection between the formal definitions in terms of the Hamiltonian with things that have a direct operational meaning through this discussion that that we just had. So by calculation, we can prove that little m agrees with big M, little j agrees with big J, and in fact those definitions are not just something that has some formal validity. It's something that really does reproduce the other notions of mass and angular momentum that we may have had based on our experience and based on the operational side of things. So it's not just pretty, it's not just something that comes out from a beautiful formal analysis, it's something that does have operational meaning. And more importantly, it's, those definitions are very powerful because they don't rely on, staring at a metric in a specific coordinate system. They don't rely on doing all sorts of other work by, looking at the geodesic equations and looking at how orbits behave. You can apply these formula for any metric in any coordinate system and, get the results. And this way you'll know what the parameters in your metric mean. And sometimes it could be that a combination of parameters is what you mean by mass, and another combination of parameters is what you mean by J. And by identifying those relationships, well, you can come up with a decent interpretation for your metric. Right? So, any questions about this? Okay, so this the result of this calculation is something that you'll find in the book, and I'm inviting you to check that on your own.
Is there a special name for this coordinate system?
Those are harmonic coordinates, or it's either called harmonic or Dedunder. It's the coordinate system that you get when you worked in linearized theory and you impose that the divergence of the trace reversed metric perturbation vanishes, and the metric perturbation is this quantity right here. So when you impose this gauge, you find that all the field equations end up looking like, in the stationary case, Laplacian type equations for your trace reverse perturbation being given by the I think there's a 16 pi. In terms of the energy momentum tensor. So you end up solving those Laplacian type equations, but here, of course, the right-hand side is 0 because we're working in vacuum, and this construction basically gives us the most general solution to Laplace's equation, except for the additional freedom we have to treat the coordinates, which was used here to get rid of all sorts of other terms. Right? Other questions? Okay. So the metric I introduced here, so in fact had some restrictions to it. So those definitions, in fact, don't care about whatever symmetries the spacetime may have. And in fact, so for example, to define an angular momentum, you don't really need to have axial symmetry. So and to define a mass, we don't really need to impose time translation symmetry. So those definitions are really robust. You don't need to impose any symmetries in your space-time. But at the level of this metric, we imposed that it was a stationary body. And we've also taken that body to be axially symmetric. So that's something I didn't spell out. But in fact, symmetries were incorporated in that metric. But I could have relaxed at least some of those symmetries. I could have relaxed the axial symmetry and produced a more complicated version of that metric. And in that case, we would have had more than one angular momentum parameter. And the connection between big J and little, big J and all the little j's would be made by making sure that we correctly identify each axis of rotation in that equation separately. So we have one definition here for each choice of rotational axis as described by this vector over here. So all the little j's that might be found in the metric would correspond to different big j's that would be defined differently because of the different choice in rotation axis. But anyway, let me stick with stationary and axially symmetric spacetimes. And for those, while the asymptotic structure of the spacetime is going to be described by this kind of metric. But if I stick with those symmetrical spacetimes, if I stick with a stationary and axially symmetric spacetime, I can do a little bit more than what I've just done. And it turns out that I can introduce alternative formal definitions for total mass and angular momentum. And I'm going to do that here. They're going to, all of this will turn out to be equivalent, but the new alternative definitions will depend, will depend very much on the existence of killing vectors. None of our definitions so far, well, especially the Hamiltonian ones, cared about the existence of killing vectors. But if we do have those two killing vectors, then we can come up with alternative definitions which have their own advantages. the main advantage that we're going to see for those definitions is that they can be turned into volume-type integral definitions, and we can see, well, the relationship between the surface definition versus the volume integral definition. So that's pretty interesting. Okay. So for stationary and axially symmetric spacetimes, we have Killing vectors. Here, by the way, in this discussion, I had the stationary assumption and I had the axially symmetric assumption only in the asymptotic portion of the spacetime, and it could have occurred, for example, that there would be some time-dependent processes inside in the bulk and deviations from axial symmetry in the bulk, and none of this matters when we go all the way to infinity, and those symmetries emerge as an approximate symmetry that is, that applies out close to infinity. But here I'll be talking about spacetimes that are stationary and axially symmetric everywhere, so I'll need that in the bulk as well. So for stationary and axially symmetric spacetimes, we have Killing vectors. We have the Killing vector associated with time translations, and we have the Killing vector associated with rotations. And we know that the metric will be, will have a vanishing Lie derivative along those directions. So we have Killing vectors, but we also have alternative definitions for mass and angular momentum. And in fact, I can come up with those surface integral definitions, which look like this. So again, it's going to be defined in terms of a closed-to surface that we're pushing all the way to infinity. And what I'm going to do is to calculate the gradient of the time-like Killing vector field, and I'm going to integrate this over that to surface using the directed two-dimensional surface element on that surface. And for angular momentum, I will define my new definition for angular momentum is going to be 1 over 16 pi. There's a factor of 2 difference and a minus sign difference. Again, we have a two-dimensional surface that we push all the way to infinity. We take the gradient of the rotational Killing vector, and we integrate that over the to surface. And here the directed surface element is going to be basically in the directions along the two normals. There's going to be a time-like normal and a space-like normal to my hypersurface. So going back to stuff we did back in chapter 3, we have the antisymmetric combination between the two normals, and then we integrate over the to surface in the usual way by using the induced metric on that to surface. And one thing to remember is that by virtue of Killing's equation, we have that each Killing vector satisfies the Killing equation, which tells us that this tensor field here is antisymmetric. And what we have here is an antisymmetric tensor field integrated over an antisymmetric integration measure. So we don't lose any information by doing this product. This antisymmetric thing would only pick out the antisymmetric combination here, but there's nothing more to that than the antisymmetric combination because of Killing's equation. So those are alternative definitions for mass and angular momentum that are appropriate when we have a time-like Killing vector, and these guys were introduced or figured out by Komar, and they're known as the Komar formulas for mass and angular momentum. Well, this looks a little bit like, coming out of the blue. But in fact, you can motivate those definitions. Of course, it helps when you know the answer. But you can motivate this by thinking, for example, in terms of the mass. You can define the mass in terms of what force you would need to provide to a stationary observer to keep that observer in place. So if I keep a particle in place in a space-time with mass, I know that I have to compensate for the gravitational attraction of the mass, so I have to apply an external force to that. So you can basically define the mass in terms of that external force that I have to provide to keep this chalk from falling down toward the surface of the Earth. So thinking along those lines, if I keep my chalk stationary by holding it in place, I know that its world line is going to be tangent to an orbit of the killing vector. So by keeping it in place, I'm aligning its forward velocity along the killing vector. So the forward velocity of that chalk is going to be proportional to the killing vector, and the acceleration of that chalk is going to be proportional to the gradient of that killing vector. So you can sort of see where all those pieces are coming from, and when you work through this argument and relate the acceleration of that piece of chalk as described here, and the force that you require. So the force that I need to apply to the chalk to prevent it from falling down is going to be the mass divided by the radius squared. Well, the radius squared is going to be provided very nicely by the integration measure. So here I multiply by r squared. Here I get the acceleration. It goes like 1 over r squared. What's left over is the coefficient in front, which is the mass. So by just doing a simple argument like this, you can sort of figure it out that those definitions are not crazy, and they're pretty well motivated. The one for angular momentum requires a little bit more thought, because now you have to think of, well, the rotational effect that would be associated with that, and those are not quite as obvious as the acceleration provided by your mass, but by analogy you can sort of see how it would work. But ultimately, the way to justify those definitions is to say, well, do they work? And again, you can say, well, those are formal definitions. They're as formal as those ones were, and we had to validate those definitions by making sure that they agree with whatever operational definitions we might come up with. So basically, the option here is to just say, okay, we're going to validate them as well in the same way by making sure that this metric, when we plug that into here, actually also produces this relationship right here, where this m agrees with little m, this j agrees with little j. You would find, and I do that in the book again, I'll skip the details because it's just routine stuff. You would find that, again, we have agreement between those formal definitions and the operational definitions, and because we have agreement here and here, we also have agreement here and here. So another calculation you can do is you can say, in a space-time with killing vectors, if I evaluate this, do I get that? And the answer is yes. So it all comes out. And so you can do it in any order you want. Basically, you can recover that, you can recover the conclusion that for stationarily and axisymmetric spacetimes, that is, when you have spacetimes admitting those two killing vectors, those definitions can be expressed in this form here, where you now involve the killing vectors directly and explicitly. These integral definitions have advantages. So in terms of computations, this is easier to deal with than that, because you don't have to do embeddings, you don't have to calculate extrinsic curvatures. So all you have to do is to figure out what the killing vector is and calculate gradients and do the rest of it. So the steps here are very simple. So when you do have a stationary and axially symmetric space-time, this is really the way to go. This is more robust because it holds in more general situations. This is also something we'll encounter later, because it turns out you can prove theorems using this form, and it's a useful starting point to prove all sorts of things. For example, when we're going to do black holes starting next week. Yep, question?
So I was under the impression that, say, for Schwarzschild, I could do it for any r equal constant surface.
True. Yeah. In fact, yeah. So here I take the limit, but in fact you can prove that the result of the integral is independent of the shape or position of the surface, provided that there is no matter in your space-time. So if you're in a vacuum region, you can reshape the surface, you can shrink it or expand it, and it doesn't matter, and that's a consequence of conservation equations. In fact, we'll look into that in just a second, so that connection. So you're right. So I didn't really need to think of the limit here, but the only caveat is that I have to be outside of matter. In other words, if I were inside of matter, of course, there would be a dependence. Yeah, but good point. Thank you. Okay, so I'll ask you to believe me, or I'll ask you to go home and do the checks for yourself. But the point is that you can insert this metric into this calculation. In this coordinate system, the time-like killing vector is just given by the time direction. The rotational killing vector is just given by the phi direction. So they're given by these guys. So you can take those vectors, you can calculate gradients. In this coordinate system, r, the vector r is also going to be, apart from a normalization factor, a vector that's aligned with the radial direction. And n here is also going to be a normalized version of the time-like killing vector. So you can quickly put all the ingredients in place, do the calculation, and recover the fact that for this metric, we have agreement between the formal and operational definitions for mass and angular momentum. So that's a check that I'll ask you to do by yourself. I go through that in the book. So we'll just admit that that this is true. Those definitions allow us to relate those surface definitions to volume integral type definitions. So in that specific context where we have a stationary and axially symmetric spacetime, we can actually turn these hypersurface integrals into volume integrals. And that's the only context where we can actually do that. We can do that also in the context of spherical symmetry, but that's a very restrictive context. Here we don't have to have spherical symmetry, we need axial symmetry. But in fact, we can turn those surface integrals into volume integrals by appealing to Stokes' theorem. And that's what I'm going to do next. So Stokes' theorem relates the surface integral of an antisymmetric tensor field to its divergence, to the volume integral of its divergence. So here we have an antisymmetric tensor field integrated over the surface. So we can, as a matter of mathematical identity, rewrite all of this in terms of a hypersurface integral of the divergence of that antisymmetric tensor field. So I'll go through this exercise because it's pretty informative and it's pretty interesting what it tells us. So let's quote Stokes' theorem. So it says that for an antisymmetric tensor field, B alpha beta, the closed two-surface integral of the tensor field is going to be twice the hypersurface integral of its divergence. So here the picture is that we have a hypersurface that's bounded by a surface S, and we can relate the surface integral to the volume integral inside S. So here we have that two-surface, which is a surface that we imagine is a nice round, topologically, topological two-sphere, close to infinity, and it encloses all of space-time, or nearly all of space-time. So I can relate this surface integral to the complete volume integral inside that closed two-surface. So let's see what we get. What I'm going to need to do, of course, so B alpha beta is going to be identified with the gradient of a killing vector. And here I won't label it. It's either t or phi. So I'll just do the calculation simultaneously for both for the time being. And when we calculate the divergence of that tensor field, we calculate two derivatives of the killing vector. I can change the order of I can change the ordering of indices here. So this is going to be the wave operator acting on my killing vector. And that's something I hope you remember from your first homework assignment, something that can be expressed in terms of the Ricci tensor. So just to make sure that I have the signs right, this is equal to plus. We cancel out this minus sign, and we get the Ricci tensor multiplying the killing vector back. And I'm going to use the Einstein field equations and relate the Ricci tensor to the energy momentum tensor of the space-time. So we get our 8 pi, we get T alpha beta minus a half T delta alpha beta, and all of this multiplies the killing vector. All right, so that's what's going to be inside the surface integral. The other thing that I will need is an expression for the directed surface element on the hypersurface, and that's going to be minus the normal vector times the usual integration measure. And if I put all of those things, what I find is that the surface integral of grad c d s beta is going to be minus. There's an overall minus sign that comes out. There's going to be an 8 pi that comes out. And apart from that, we're going to have the hypersurface integral of the energy momentum tensor multiplying the normal vector, multiplying the killing vector, whichever it is, and we integrate that over the surface. Right? Oh, I forgot a factor of 2. So there was a factor of 2 here that I forgot. And with that, I can re-express my mass as a volume integral definition. So the mass now becomes minus this over 8 pi. So I pick up a factor of 2, kill the minus sign. And now I'll indicate that my killing vector was actually the timelike killing vector. And the angular momentum, we keep the minus sign, we get rid of the 16 pi. We have another hypersurface integral. This time involving the rotational killing vector. And those, for stationary and axially symmetric spacetimes, are pretty much equivalent definitions for mass and angular momentum. But now, instead of dealing with a closed two-surface integral at infinity, we decide to do the full hypersurface integration, and that allows us to define essentially what is an expression. It allows us to define what is a mass density for the spacetime and what is an angular momentum density for the spacetime in terms of an energy momentum tensor. So this combination of things here inside the integral can be interpreted here as a proper mass density. And this combination over here can be interpreted here as an angular momentum density. And it's pretty plausible that while it should sort of be tied to where the energy momentum tensor is, what is not obvious is the fact that the density should involve not the energy momentum tensor itself, but this sort of trace reverse combination that occurs in the field equations. That's not something that I think any of us would have guessed, and that's not something that, appears to be particularly compelling, but it's something that must be, must be there. It must be that if the surface integrals make sense, which they do. If you insist in turning those surface integrals into hypersurface integrals, then you have to recognize, you have to live with the fact that the proper density is not really defined in terms of an energy momentum tensor by itself, but it has to involve this combination. Sometimes you see people trying to come up with, a way of giving a physical motivation for this or physical interpretation. We know that, that the entire mass energy is not just the energy contained in the matter distribution. There's also gravitational field energy that has to go into this. So in that sense, you have more ingredients here than just coming from the energy momentum tensor, and that's a way of sort of reflecting the gravitational energy content of the total mass and also the total angular momentum. Well, the problem is that when you start using this language, it becomes sort of meaningless. We sort of know what we mean, physically speaking, but if you ask anybody in GR to give you a precise notion of gravitational field energy, they will either fail if they're honest, or they will, be dishonest if they tell you they have an answer, or they're just incompetent. Again, I'm being taped, and I know I'll get in trouble for this. There's been generations of people trying to come up with definitions of gravitational field energy in GR. None of that makes sense because there's just no such thing. There's no such thing because, if I can free fall in the gravitational field and remove all local aspects of gravity in my frame, in my reference frame, there's no way that I can assign a meaningful notion of gravitational field energy that wouldn't be completely unambiguous or completely frame dependent. If you can switch off gravity locally, you have to also be able to switch off its field energy locally. And that tells you basically that that notion has to be frame dependent if it exists at all. And it's better to say that, well, it doesn't exist at all. It's just something that we can use in a physical discussion if we insist, but it's not terribly well defined. It just conveys a sort of warm and funny feeling that says that, that matter should be exchanging energy with the gravitational field, but we really don't know what we mean when we say that. It sounds good. It's probably right, but it's completely ambiguous and not well defined. All right. Any questions about this? I've assumed one thing here. So a couple of remarks first. So when you deal with this hypersurface integral, it's pretty clear that you don't need to consider a hypersurface that extends beyond the matter distribution. Right? So if the matter distribution lives here on your hypersurface, well, you can consider a hypersurface that just basically hugs this matter distribution, and that'll do the job. Or you can consider a hypersurface that goes well beyond the matter distribution, and it doesn't make a difference because the integral here only cares where you have matter, and any, the contribution to the integral coming from outside the matter will be zero. So it really doesn't matter how far you extend the hypersurface. Well, if you know that, then you know that it won't matter what shape you give the hypersurface once you're outside the star. You can give it any shape, you can give it any radius. All of those extra contributions will be zero. And the point of all this is that, well, that's the proof that, that the choice of two surface that we started with, so long as you're outside the matter, the choice of the two surface is irrelevant. Any two surface integral evaluated on any two surface outside the matter distribution will return exactly the same expression, the same value for the mass and angular momentum. So that's something that could be proved at the level of the surface integral, but I think it's really obvious when you look at it from this definition, from this alternative expression right here. So that's the answer to your question that it didn't matter here where I pushed, what kind of two surface I picked and where I put it. It doesn't matter so long as you're outside the matter distribution. Typically, it turns out to be simpler to work far away because the metric simplifies and the calculations simplify when you're working far away from when you're working in the asymptotic region. So that's one remark. The other remark is that I've made an assumption. I've made an assumption here that my hypersurface up here was bounded by only one surface. So basically, I was assuming that there were no internal boundaries that I should worry about. So if I'm dealing with a regular star, that's perfectly fine. I can extend the, so I can have a bounding surface, and I can extend the hypersurface everywhere, cut across the star, go all the way to the center, and I never meet a problem. I never meet an obstacle. I never meet a singularity. But if I'm doing this with a black hole, I may encounter some difficulties. So I still have that bounding to surface, but if I have a black hole in here, maybe I don't want to go inside. And I can avoid going inside by cutting off the hypersurface inside an internal boundary. But if I do that, I'm changing the answer. Because if I have a hypersurface bounded by two boundaries, one internal, the other one external, this relationship changes because I need to account for all the boundaries when I invoke Stokes' theorem. So in a situation like this, we would find that the surface integral at infinity would be relatable to the hypersurface integral truncated here, but we would still have to account for what's inside that boundary surface, and what we would have in this case is a relationship between the hypersurface integral and a term like this for each bounding surface, for each boundary. So in that case, the equality that I wrote down here would be modified. We would add a term here coming from the internal boundary, and we would have a term here coming from the internal boundary, and those would be exactly the same type of definitions, except that now the surface integral would be taken over the internal boundary. So this business of relating the two-surface integral over a hypersurface integrals only works if you're dealing with perfectly regular hypersurfaces and you don't have obstacles, you don't have handles, you don't have topological issues, and you don't have singularities, or you don't have black holes, or you have none of these things. So those are pretty severe restriction, and again, it goes to show that the definition in terms of the outer two-surface is very robust, and you need all sorts of fine print and additional conditions to make sure that a hypersurface integral like this will be well defined. And typically, if you have a topological structure here, or some handle, or some obstacle, what you would need to do is to carve it out, and you would add additional terms in your Stokes' theorem to account for the initial boundaries. So when we do that for black holes, and we will do that for black holes, I will add those internal terms, and those would be basically boundary integrals on the event horizon that we include to relate the mass asymptotically to the mass I might measure just outside the black hole, and whatever is left behind, whatever lives between the black hole and infinity. So in that accounting, basically, you can write down the total mass of the space-time in terms of what's inside the black hole as bounded by that internal boundary, plus whatever matter lives outside the black hole, where the hypersurface here would extend from the black hole all the way out to infinity. So we'll encounter things like that in the last portion of the course. All right. So the message here, the important points are that under some circumstances, limited circumstances, we can actually turn those two surface integrals into volume integrals. And we have a case right here. The density that we get out of all this might not be a very intuitive density, but it's the density that you need in order to make all of this work. So the density of mass and the density of angular momentum in the space-time are really given by those expressions over there. And those may not have been the expressions I would have guessed if I had been tempted to provide, volume integral type definitions for these things. I would probably get it wrong. I probably would not have inserted the trace term inside the integral, and because of that, I would get it wrong, basically. All right? All right. I have time to do one more thing and wrap up the chapter. So I want to talk about mass transfer, and I want to talk about angular momentum transfer, something that will play an important role in the black hole discussion. Okay, so we're still talking about stationary and axially symmetric spacetimes. So we have a stationary plus axisymmetric spacetime, which means that we still have two killing vectors. And what I want to consider here is a test energy momentum tensor doing something in the spacetime. So it's an energy momentum tensor that's very small, that doesn't participate in building up the curvature of spacetime, but it represents some flow of matter in my spacetime. And to that flow of matter, I want to associate a flow of mass and a flow of angular momentum. So we have a test, T mu nu, that represents a flow of matter in that spacetime. And from that, I want to calculate a transfer of mass and angular momentum across a hypersurface. So if I, take a hypersurface, for example, a hypersurface of constant time or a hypersurface of constant spatial coordinate that has, a two-dimensional cross-section and extends over time, I want to keep track of how much matter is crossing my surface, and I want to account for how much mass has been transferred and how much angular momentum has been transferred. That's what I want to do. And that's something that we will need when we start talking about the first law of black hole mechanics, when a black hole might acquire some new material, and we want to calculate how its mass changes and how its angular momentum changes as a result of this accretion process. So I want to come up with reasonable formulas that describe this transfer of mass. So just to motivate the definitions or the formulas that I'll give you for this, I'll just take a specific example. So we'll consider a pressureless fluid. Which means that its energy momentum tensor is going to be given in terms of a mass density and a velocity vector, but there's no pressure term in the energy momentum tensor. So this is just an example, just to basically illustrate or motivate the definitions. And but what I'm going to do is going to apply to any energy momentum tensor. It doesn't, it's more general than what I'm doing now. So we're going to look into that and see, if we can come up with a decent notion of transfer of mass energy and transfer of angular momentum. So this energy momentum tensor is going to satisfy energy momentum conservation. So I'm going to impose that the divergence of that energy momentum tensor will vanish. And when I calculate this, I'm going to find, first of all, that when I evaluate the partial derivatives, the covariant derivatives, I find that I'll get a term involving the acceleration of the velocity field. And then I'm going to get another term involving I want to have u beta here, the divergence of this vector field right here. So this is what I get when I calculate the covariant derivatives of this. This is, of course, the acceleration of the particle of the fluid elements. So I have something involving the acceleration. I have something involving this divergence over here. The acceleration is always orthogonal to the velocity vector. So those pieces are orthogonal to each other, and they must vanish individually if the whole thing is to vanish. So as a result of energy momentum conservation, I find that the acceleration of the fluid elements must vanish. There's no pressure gradient to create an acceleration. So we get geodesic motion for the fluid elements. And on top of that, we get that the vector J alpha, which I'll define to be rho u alpha, is conserved, or it's divergence free, as a consequence of the energy momentum conservation. And the interpretation of this vector is that, well, this is really the density, the proper density of the fluid, so it's the density of rest mass in its own frame. So this is really the flux of rest mass for the fluid. And this conservation statement then is just a statement that the rest mass of the fluid is conserved as the fluid moves around in space-time. Okay. The rest mass energy of the fluid is going to be a form of the energy carried by the fluid, but it's not all there is. To get the energy, carried by the fluid element, we have to think of the conserved quantity that's going to be carried by the geodesic motion of each fluid element, and that will involve the killing vector. So we've seen all of this before. There's nothing new about this. So the killing vectors give us other conserved quantities. We have the conserved quantities. We have one that's the energy per unit mass in the fluid, or the energy per unit mass of each fluid element. That's going to be given by the velocity dotted with the killing vector. And that's a conserved quantity along the fluid, along the motion of each fluid element, because each fluid element satisfies the geodesic equation. So each fluid element moves on a geodesic, and that guarantees, by virtue of Killing's equation and the geodesic equation, that this is a conserved quantity along the motion of the fluid elements. And we have another one, which is the conserved angular momentum, which is the contraction of the velocity vector with the killing vector, the rotational killing vector. Okay. This is the energy per unit rest mass. This is the angular momentum per unit rest mass. So if I want to combine these things into a vector that will describe the transfer, the flow of energy, what I have to do is to take the flux of rest mass, multiply by energy per rest mass, and I get a flux of energy. So the energy flux vector will be the mass flux vector multiplying the energy per unit mass. So what is that? Well, I just take my J alpha and I multiply by E tilde. And that's a vector I'll call epsilon alpha. So epsilon alpha, by definition, is the energy flux vector associated with transfer of energy. And that energy, of course, accounts for not just rest mass energy, but all the other forms of energy that the fluid might carry, like internal energy, in the thermodynamic sense. So having this, I can rewrite it in terms of what E stands for. So I have a minus sign. E stands for U beta, C beta. And then I have a rho U alpha. So what we see coming out of this is the energy momentum tensor multiplied by the Killing vector. So that contraction, that component of the energy momentum tensor is something that has an interpretation in terms of an energy flux vector. And not only that, but we can verify that this vector is conserved in the sense that its divergence is going to be 0. Its divergence is 0, again, by virtue of energy momentum conservation and Killing's equation. So we get a 0 term because of energy momentum conservation, and we get another 0 term by virtue of Killing's equation, because Killing's equation tells us that this combination here is antisymmetric, but it's multiplying a symmetric tensor. Therefore, we get 0 on both counts, and this is a conserved vector. So what I wanted to get here through this little illustration is the motivation of this as an energy flux vector. Well, we can do it for angular momentum. So the angular momentum vector flux vector, and I'll introduce the notation L for that, L alpha. Well, that's going to be the rest mass flux vector multiplying by the angular momentum per unit mass by the same argument. And this is given by the energy momentum tensor dotted with the rotational Killing vector. So again, by the same argument, this is also a conserved vector. So now we have the energy flux. We have the angular momentum flux. And those vectors are conserved in the sense of having a 0 divergence. Okay. So we have vectors that represent a flux. And a flux, in the traditional sense, a flux vector is always something that represents the transfer of something across a surface per unit time. So if I want to define, a sensible notion of a flux of, a transfer of energy and a transfer of angular momentum, presumably what I would need to do is to integrate this over a hypersurface. And if I do it for a hypersurface of spatial position, I would integrate over the area associated with that surface and integrate over time as well. So it's a process. This is a per unit surface, per unit time type of thing. So the claim is that the transfer of energy, mass energy, I should say, across a hypersurface sigma, or some finite hypersurface sigma, is going to be obtained by taking my flux vector and integrating over the hypersurface. And that stands for T alpha beta time like Killing vector multiplying the surface element. And the transfer of angular momentum That's going to be given by the same type of hypersurface integral, now involving my flux vector L. So here I get a plus T alpha beta C phi integrated over the hypersurface. I might as well call that, definitions of what I would mean by the, transfer of mass across the hypersurface. So, just as an example, just to firm up our understanding of this, if I go back to my fluid and I choose to take a hypersurface of constant time in the sense of being orthogonal to the fluid lines of the fluid element. So, for my fluid, the pressureless fluid, I can consider a hypersurface sigma that's orthogonal to the fluid lines, to the fluid, word lines. So my fluid word lines would give me a congruence of geodesics in my space-time, and here I'm imagining that they're hypersurface orthogonal, and I'm calculating the transfer of mass across that hypersurface. The surface element on that hypersurface will be in the direction of the normal, which is aligned with the velocity vector. So I get the usual minus sign because, again, it's that epsilon thing that always occurs. So I have a surface element that's going to be aligned with the velocity vector, and then I get the usual thing involving the square root of the induced metric on the hypersurface, and I'm integrating over the hypersurface. So if I do that, delta m, I lose the minus sign on the right-hand side. I get T alpha beta. I get U alpha C beta. And I'm integrating over the hypersurface. For my energy momentum tensor, I will get, so when I consider the contraction, I get, I'm losing my board. I will get rho, I will get U alpha multiplying U alpha, I'll get a minus 1. And I will get U beta multiplying C beta, I'll get minus E tilde. So in that example, I end up with rho E tilde integrating over the hypersurface. And what does that mean? Well, I know that this is the mass density, the proper mass density in the frame of the fluid, rest mass density. This is energy per unit mass, so this is really the density of energy across the hypersurface. And that's what I'm integrating over the hypersurface. And that is the transfer of mass across that hypersurface. Right, so the transfer of mass across a hypersurface that cross all the lines of the fluid is basically the amount of mass that the fluid is contributing in that spacetime. And that definition seems to be sensible. It reproduces what it ought to reproduce. So that's a flux across a space-like surface. If we had a time-like surface and we had flow lines that go like this, then basically the flux would be something that involves, crossing this hypersurface over time, and we would calculate how much mass has been transferred over time by doing the integral over the full hypersurface. So it would involve basically a cross-section integration together with a time integration in that direction, as we move along with the hypersurface. Okay, so basically the bottom line of this is that here we have sensible notions for transfer of mass and angular momentum across a hypersurface when we're given a space-time with two killing vectors, and provided that the energy momentum tensor that I'm talking about here is not something that participates in the space-time curvature. For all of this to make sense, it's important that that the energy momentum tensor describes, distribution of test matter in the space-time. And I wanted to get this out of the way because, again, as I told you, when we do, when we talk about black holes and we talk about the formulation of the first law of black hole mechanics, well, we will be interested in a physical process where the black hole acquires mass, acquires angular momentum, and those are going to be, expressions that will tell us, for a given test energy momentum tensor in the black hole spacetime, how much is being absorbed by the black hole. Just one final remark before we break. We have conservation statements for those vectors. And if we invoke Gauss's theorem, what those statements say is that if we had a closed surface, sigma, then the flux across the closed surface, the transfer of mass across the closed surface would be 0, and the transfer of angular momentum across the closed surface would be 0, and those statements would be true for closed sigma. And the interpretation here, I think, is pretty clear. If we have a closed surface like this in space-time, whatever crosses here will have to come out again. So by the time you're done integrating over the whole surface, the positive contribution you got here will be compensated by the negative contributions you had there. And basically all the mass that's transferred through, there's no mass that's leaking inside or captured inside. And that would be true for angular momentum. So if you cross like this, you'll get out again. If you cross like this, you'll get out again. And so the complete accounting of all the mass transfer for the closed surface will be 0. Yep.
We're still assuming that our hypersurface has no holes in it, like no.
Yeah, that's right. If there were, if there was an internal cutoff or boundary inside, then that surface integral would have to, So basically, so if I had an internal boundary in here, then my actual closed surface would be the original one plus a channel that I dig to the internal surface, and the statement then would be that what goes through the outer boundary minus what goes through the inner boundary would be 0. Yeah. So if stuff comes in, it comes in here. Part of it might escape here. Part of it might cross here. All of that, if you account for the real, if you account for both boundaries, then you find that the total accounting is 0, as we had before. So yeah, the Gauss is pretty flexible, right? So if you're given a whole bunch of boundaries, you can always turn that into a single boundary by digging those channels, very narrow channels that don't contribute anything. So you just dig some channels like this, and after that you find that you have only one closed surface that surrounds everything. And but of course, when you write down the integral, you'll find that you'll get a contribution from the outer boundary and contributions from the inner boundaries. But all of this comes from this overall combined boundary that is simply connected, and all of that defines a simply connected region inside. So, good point. So you can always adapt these things for whatever situation you need. Okay, so I think I'm done for today. So this really wraps up chapter 4. So now we have really all the tools we need. Next week we're going to get started with black holes. And I'll start by reviewing the elementary stuff about black holes, but then we'll go into black hole mechanics and things that really are generic to all black holes. And I think we'll have a lot of fun. All the investment that we've made so far in the semester will be coming to fruition, and we'll see how we involve all of these things to do black hole mechanics. All right, so any other parting questions before we break? Okay, so I'll see you next week.